and welcome to this series, Know About Research in ISHRAE. This is our third webinar of the series. And today we have with us Dr.K.Srithar, who has been the principal investigator in the ISHRAE funded project. So he is going to share with us his experience as a researcher on this project, as well as the outcomes from this project. So before we go into the presentation, I'd like to introduce Dr. Srithar. He is professor and head of mechanical engineering at Tyagaraja College of Engineering. He has a ME in thermal engineering from Annamalai University and a PhD from IIT Madras. In addition, he has been awarded a postdoctoral fellowship through the Endeavour Executive Award, a highly prestigious award by the Australian government, and he completed his postdoctoral research at the Australian National University in Canberra. During the year 2021-22, he served as president of the Madurai chapter of ISHRAE. He has published 72 papers in reputed international journals during his teaching and research career. He has presented 14 papers at international and national conferences and has a total of 35 years of teaching experience. During the year 2020, he was named one of the world's top 2% scientists, most influential scientists, single-year impact in a survey conducted by Elsevier and Stanford University. His position in the AD Scientific Index of 2023 places him among the top 5% of scientists in Asia and the top 10% of scientists worldwide in the field of heat pipes. Besides, he has written a book as a co-author for Tata McGraw-Hill, and he has been selected as an Endeavour ambassador to promote higher education among Indian students in Australia. So welcome, Dr. Srithar.
Thank you, madam.
I would like to add that I think I put a message also that 2 papers have been published in Elsevier publications from the results of this project. So welcome, Dr. Srithar. You can go ahead, start.
Thank you. Thank you very much, madam. Good evening to all. This is a presentation about one of the project outcome from getting from the ISHRAE project, cold storage operated by solar energy. The main objective of this project is to enhance COP of the cold storage a little bit by means of having an additional cooler before the condenser, as well as having another heat exchanger to place before the evaporator, before the compressor. So in one part, more amount of heat is liberated. That is what we call as subcooling, which causes more refrigerating effect in the existing cold storage. Another thing is to retrieve the chillness from the refrigerant, which comes out from the evaporator by means of placing a heat exchanger, which causes a condensation of water. So we are going to integrate a HDH, what we call as humidification, dehumidification, desalination, for recovering the heat from your VCR system. So that is the first objective of this experiments. Then the entire cold storage is going to operate by means of a PV model, and for increase the efficiency of the PV model, existing PV model, we are using the heat pipe technology and fluid flow cooling. We are using both air and water flow, and we check the optimized parameter which can be used for better performance. And finally, we implemented in the pilot plant. So this is the objective of our work. Actually, this is a TS diagram, the basic TS diagram, ideal cycle of vapor compression. Actually, 1 to 2, that is ideal compression in the compressor. From 1 to 2, 2 to 3 is the cooling takes place in a condenser. That is from high superheated vapor is condensed to saturated liquid at the same pressure in a condenser. Then 3 to 4 is the expansion takes place in a throttle valve, and after that it enters to the evaporator, where refrigeration effect causes an cooling effect in the refrigerator space by means of absorbing heat from 4 to 1 process. So that is the ideal cases. If you by means of any type of additional cooling, if you are cooling from 3 to 3 days, that is we call a subcooling liquid, the refrigerant saturated liquid into subcooled liquid by means of providing some additional cooler heat exchanger, then definitely the refrigerating effect will be improved. Instead of from 4 to 1, the refrigerating effect is increased from 4 dash to 1. So that is the first advantages of the placing a cooler in between the condenser and the compressor. Then another heat exchanger, that is dehumidifier, what we call as dehumidifier of a HDH desalination, that will be placed in between the evaporator and compressor. This causes the additional little bit heating of the input refrigerant vapor which enters the compressor. That is from saturated vapor of state 1. Now it is increased to some little bit degree to 1 dash. This causes some little bit reduction in work. Therefore, we have an increase in refrigerating effect. At the same time, we have a small reduction in work. This causes increase in COP. So that is the objective of our experimental work. For that, first we are the main task behind us is to design a heat exchanger for the cooling of the condenser by using a water cooler. Actually, we are using a water cooled condenser, simple double pipe heat exchanger, a tube heat exchanger. That is the first challenge for us. To increase the heat transfer rate between the heat exchanger inside the fluid as well as refrigerant, we have to place a insert. So suitable insert we have designed, and that insert will be tested in a model test rig. So this is a test rig. We have a small chest refrigerator, a small refrigerator, 0.25 watt of refrigerating effect of a small chest refrigerator, where it is connected with the condenser and HDH desalination system. So I will explain one by one. So this is the compressor. From the compressor, before it enters to the condenser, we have a pre-cooling effect is there. So you have a heat exchanger. The red color is a heat exchanger, where inside you have the refrigerant tube, which is directly passed to this condenser. Outside the heat exchanger, we have a water cooling effect. This water is pumped by means of a pump at the bottom. So here you are having a water pump. This water is circulated through the heat exchanger, absorb heat from the refrigerant, and again this refrigerant is sprayed at the top level here. At the same time, we have a cold air which we passes through this pipe, and this is moving from bottom to top. So simultaneously, water is passing through the top to bottom, and air is passing through the bottom to top. Therefore, we are having a moisture. Actually, here we are only trying for the cooling of the condenser. So we don't have HDH desalination system only for cooling tower. So this is a cooling tower with a packaged material, and that cooling tower waste, that water will be again collected here, and again it is pumped like this. This is a setup diagram, and we are using some 5 to 6 different mass flow rate, and we are using some different insert like this. So these are the insert we are placing inside the heat exchanger. There are plain buffle. This is what we call as a plain buffle, and that same buffle we are having holes at the buffles, and the buffle will have a strip cut, that is a rectangular cut, and this is called as a section cut. There are 4 types of insert. These insert are designed based on to have a very high heat transfer rate. At the same time, it has have a very low friction, thereby low pressure drop. So pressure drop should be low. At the same time, heat transfer rate should be high. This can be measured by means of a parameter what we call as thermal enhancement factor. This is a measure of directly the ratio between heat transfer and friction. So based on that, we designed some 4 insert, and the 4 insert are connected with the continuous arrangement like this. So that is a diagram where it is fitted inside the condenser. Inside the tube, you have a refrigerant vapor, which is coming from the compressor, and outside you have a water cooling effect. We have 6 different mass flow rate we have tried, and 4 different load we have given to the refrigerant space. Refrigerant space, we have 0 load and quarter load and 50% of load and full load. So that is we have tried, and based on that, what we got the outcome is the last buffle, that is buffle with the internal suction dead, have the better performance. And mass flow rate, higher mass flow rate will gives the better mass COP enhancement. So compared to lower mass flow rate, higher, that is 0.427 kg per second of flow rate of water, will gives more evaporation, more COP. That is the second finding. Conventional refrigerator will have 0.9384 COP alone, whereas when I go for modified additional of a condenser with a bubble with the internal suction tank, they are having a COP increase in COP of 1.1049. There is nearly 75% of increase in for the 75% of the product load, we are having this much of increase. And also the energy consumption point of view, the energy consumption is reduced from 0.22 in a conventional refrigerator to 0.20 kilowatt hour. So that is the first thing. So for the pilot plant, we finalized a condenser with the buffle with the internal suction and that inside a heat exchanger as the first thing we decided. So that is the first outcome we are getting from a laboratory model experiment. Then we go for the design of a humidifier. Humidifier is nothing but air as well as water will be mixed with each other by means of a packing material, where we have a packing material in the humidifier chamber. The yellow color is the humidifier chamber. The sectional diagram of the humidifier chamber is given in the top as well as the right hand side. You have 3 positions to fix the packing material. What we call as packing material, we are using sponge or we can use cellulose pad. Various materials they have tried in researchers that will be get more absorption with the water as well as air. The setup principle is very simple. The air which is coming from the blower will goes from bottom to top, whereas the water which is coming from the top will be sprayed at the bottom. So we studied only the what type of packing material we can use, where the position of the packing material we can use, what is the thickness of the packing materials we can use. While searching the journals and previous literature, we found that most of the case cellulose packing material is best, having a highest moisture content of outcome moisture air. But however, that didn't most of the literatures doesn't speak about the thickness of the packing material as well as where we can fix the packing material and how many packing material we can fix. So these are the things or the research gap when we studied the experimental work while we are doing the experiments. So number 1 is varying the thickness is one of the challenge, and number 2, positioning the packing material, whether we are positioning one single packing material or double packing material, or we are these are the challenges we have found out from the literatures. So based on that, so this is the position we have packing material. We have 3 layers of position arrangement for the packing material. This arrangement will be fixed inside the humidifier. In the first arrangement, we have only packing material placed on top. The second, the packing material is placed at the middle itself. The third one is the packing material is fixed at the bottom, that is nearest to airflow. Top means nearest to water flow. And the other 2 fixations are top and middle, and top and bottom, and top, middle, and bottom. So all the possibilities we have checked. For the 5 to 6 mass flow rate ranging of water as well as 6 mass flow rate of ranging of air. So air for air flow rate we are using a blower. For water flow rate we are using a pump. The air flow rate is varying from 1.59 to 5.22 kg per minute of step size as given here. And the air flow rate is varying from 8.67 to water flow rate to 23.14 kg per minute of various step size. And layer position is shown here. We have different thickness of the packing material also we have tried, that is 25 mm, 50 mm, 75 mm, 100 mm, 150 mm. So what we are doing is we select one position, testing with the 6 mass flow rate of water, 6 mass flow rate of air, and get the result of by means of humidifier efficiency, the rise in specific humidity, relative humidity. Based on that, we compare the result for other thickness of the material and finalize the minimum which thickness is optimum. And based on the optimum thickness, then we go for placing in various positions. That is just placing one material at the top and placing the same material at the middle and placing the same material at the bottom, like that, top middle, top bottom, and bottom middle bottom, and the experiment has been continued. So this is the experiment we have did for the second case. Based on that, we got the results for like that. With respect to water flow rate, highest water flow rate will give the better results. When we fix the very highest, that is 23.14 kg per minute of water flow rate, we have a maximum specific humidity of 0.01. If we are connected with desalinated, dehumidifier, definitely it will give a water evaporation rate of 0.92 grams per second. So that is the result. So high water flow rate is better for this case, and low mass flow rate of air is better for better humidification efficiency. So water flow rate is fixed as high and air flow rate is fixed at very minimum value. So these are the outcome we are getting from the results based on mass of water vapor evaporator and specific humidity difference. That it means that the air before it enters the humidifier and the humidified air, the difference between specific humidity of the inlet and outlet of the air in the humidifier, that is specific humidity difference. So based on that, we have concluded that higher water flow rate, lower air flow rate are comfortable for getting a good results. So that is a fixed, we have fixed this mass flow rate like that. And based on the mass flow rate, we have changed the thickness of the material. Actually, this experiment results is shown for a thickness of 150 mm of thickness of packing material and for a single packing material. Then we have changed the packing material for different cases. That is the top graph shows when the packing material is fixed in the top side and packing material is fixed at the middle and packing material is placed on the bottom. Similarly, the packing material is fixed in top and middle and top and bottom and bottom and top. We have compared the result mainly based on the pressure drop as well as the outlet velocity what we are getting, because this air, moist air, has to go to dehumidifier with at least some little bit highest velocity. So we have to choose with the highest velocity of air case with the lowest pressure drop. So based on that results, we have concluded that 25 mm thickness of the material will be the best packing material, and packing material which is placed at the far away from the air inlet, that is the top position, is the best thing. So placing the packing material at top, out of the 6 graph, it gives the lowest pressure drop. Therefore, we are fixing that is a optimum one. And based on the packing material thickness performance, we are fixing 25 mm is the optimum. So first we have optimized the heat exchanger insert and pump, and we have optimized the humidifier packing material and position. Now we switch over to the main pilot plant. So this is a main pilot plant setup diagram. I will explain a small thing. This is a a compressor of a cold storage. This compressor refrigerant goes to the condenser. Before it goes to the condenser, it enters the pre-cooler. So we are fixing a pre-cooler in between the compressor and condenser. The pre-cooler is cooled by means of a water. The water is coming from this pump, from this water tank, and it is circulating through the heat exchanger. And again, it goes to the humidifier chamber. This is called a humidifier chamber, where that hot water will be sprayed. At the same time, we have a blower to pump the air. The air is going like this, and it is going from bottom to top. While it contact with this cellulose pad, better mixing takes place. Therefore, we are getting a moist air. This moist air goes to this pipe flow, where we are having another heat exchanger, which is placed in between the evaporator as well as compressor. While the chill refrigerant, which comes from the evaporator, while it contact with the moist air will be condensed. That is, the moist from the air will be condensed. What we getting a perfect purified desalinated water. So we have a condensed water, desalinated water is one of the outcome, another additional outcome by means of doing this experiment. So COP increases by means of placing a pre-cooler and dehumidifier. At the same time, additionally, we are having a distillate water as an outcome. Here also, we are changing the mass flow rate, water flow rate, as well as here we don't have any design changes in pre-cooler, because already we have proven that one type of insert is very good. Therefore, we fixed that insert there, and we have conducted various experiments, and that result I will show here. So this is an overall setup of the project. We have a 0.5 ton of refrigerator, cold storage devices we have installed with the help of ISHRAE. We have a blower here. This is a humidifier chamber, and this is the red color is a pre-cooler, which is connected in between condenser and compressor, and the blue color, this color, this is a heat exchanger which is connected between the evaporator as well as compressor. We call it as dehumidifier. This is humidifier, and various pressure drop in the condenser, evaporator, and compressor and throttle valve will be measured by means of this pressure gauge, and all temperatures variations starting from condenser inlet to condenser outlet, and the humidifier inlet, outlet, and everything will be measured by means of some 16 to 17 thermocouples, and the pressure drop also varied by means of the sensor, and mass flow rate is controlled. Air mass flow rate is controlled by means of these two valves, and water flow rate is controlled by means of a small valve here. Actually, this pump is embedded here. The pump is small pump is here. The working principle is the first circuit is the water which is coming from the pump is directly go to this pre-cooler, gets heated heat from the refrigerant, hot refrigerant, and it return back like this, and it will be sprayed here, humidifier. The hot water will be cooled down, and that will be collected in water tank. Again, it is circulated. That is the first circuit of water flow rate. For air flow rate, air from the ambient will be pumped through the blower, and it goes enter to the humidifier, and from bottom to top it flows, and the moist flow rate can be controlled by means of this flow rate, and that moist air will circulate along the refrigerant coil which comes from the evaporator. So as it contact with the chilled refrigerant coil, it liberate its heat. The moist air liberate its heat, and there will be a little bit increase in temperature of the incoming refrigerant, as well as the condensation takes place. That condensed water will be collected here. So that is the experimental setup. For loading system, we have calculated for potato. Instead of placing potato for various load, we have designed based on the ISHRAE handbook. Based on the design, we have simulated the heat by means of using a heater. Therefore, we have designed for quarter load. Normally, quarter load is approximately equivalent to 80 kg of potato. Like that, we have designed for various load and 5 different load we have checked. So a heater coil which simulates the heat produced by the potatoes. We have designed for the potatoes and the, some 5 different heat load and 5 to 6 different mass flow rate of air and water. We have conducted experiments from the given temperature to that is ambient temperature to the set temperature of 2 degree. We have taken the time taken and we have find out the power consumed by the cold storage. At the same time, power consumed by the blower and we are adding a additional blower and pump. We are find out the power consumed by the blower as well as water pump and which flow rate it will be optimum. That is, we can have a water desalinated water as an outcome. Cost of the based on the cost of the desalinated water, which thing is optimum? That is the final result we have produced. Based on conventional system, first we have run only with the pre-cooler. There we doesn't bother about the airflow rate, humidifier, HDH desalinizer. Only the pre-cooler is operated. That is only the pump is operated. What we got the result is conventional COP of the cold storage for a 200 voltage of load. That is quarter load of cold storage. It gives only 2.57 conventional, whereas we have an increase in COP of 2.77 when the mass flow rate is 8.77. And when we increase the mass flow to the highest value, we got a highest value of COP of 2.86. So net result is when we are using highest mass flow rate of water in the pre-cooler, the conventional cold storage COP is increased from 2.57 to 2.86. That is the first outcome. That is about 7 to 10% increase for various flow rate. So that is the graph shown. The graph shown between the power consumption, COP for conventional and various mass flow rate of pre-cooler with the various mass flow rate. So lowest mass flow rate itself will give better quality when compared to conventional system, but highest we can give the results when we are connected with the higher mass flow rate. So that is the first outcome we are having. Then this is the second outcome. Based on the mass flow rate as well as power consumption, these are the another results. Based on the power consumption, lower mass flow rate will consuming a power consumption of 0.712, whereas higher mass flow rate will consume a power consumption of 0.689. That is a power consumption, power saving we are getting. So based on the result, higher mass flow rate of the pre-cooler will give you a better COP as well as lower power consumption. About 3.2% of reduction in power consumption. Also, we have studied the energy related study. That is how much of consumption we have made by means of having a transmission load, respiration load, consumption charge, and electricity consumption based on that. Based on that, we are getting regular conventional cold storage will have a unit of 1,188.41 kilowatt hour, and per unit approximately cost of 10 rupees per unit. We have a maximum running cost of 1,885 of rupees for running a conventional cold storage of 0.5 ton of refrigeration capacity with a 20% load of equivalent to 80 kg of potato. So when 80 kg of potato is stored in a cold storage and is continuously running for 30 days, the total load we have calculated is 188.41 kilowatt hour, and multiplied by the unit cost, we are having the total cost of the electricity bill is 1,885. This is calculated based on the ISHRAE handbook results of cold storage. Then, when only pre-cooler is running. That is only by running a small pump with the pre-cooling the heat exchanger. We are having a total amount saving of 1,000. Where is that? Yeah, 1,861. So that is the amount of electricity bill what we are getting when a cold storage is operated with the pre-cooler. Therefore, we are having an energy saving of rupees 24 per month. Only if this 24 per month is included with the pumping power also. So that is the advantages of having a small water cooler effective by having a small water pump. So that is the first result we are getting. The second result is we have connected the pilot plant with the HDH desalination. That is a humidifier as well as dehumidifier. Here, additionally, we have a blower effect is also there. So by using the air fluid, therefore, final result, we have to compare the energy consumption by the blower also. So based on the result, here also we have obtained that higher mass flow rate of water will have a good advantages of higher COP and lower power consumption, and lower mass flow rate of air will give higher COP with lower power consumption. So that is a fact what we get compared to the laboratory model. The same result we are getting here also, and air flow rate we fix as a lower. Based on that, we have compared various packing material in the humidifier, and that is the outcome we are getting. The outcome we have compared with the desalinated water. So we have a highest desalinated water when we have a higher packing material thickness. Say for example, lower packing material thickness. When we have a 25 mm packing material thickness, for all the load, that is full load, 1,000 is full load of the refrigerator, 800 is 75%, 50%, and 25%, and 20%. So for all, 20, 40, 60, 80, and 100% load. For all the load, the lower thickness and placing at the topmost position will give the better results. We are getting a better desalinated water. So up to maximum of 800 milliliter per hour is additional. It is additional outcome of the apart from the saving of the COP, saving of producing a desalinated water of a little bit quantity is an additional effect of this pilot storage plant. And compared to the same energy saving potential, conventional will have a energy consumption of 1,885. When we have a particular mass flow rate, that is a higher mass flow rate of water and lower mass flow rate of air, will have only a electricity bill of 1,504. Nearly, we are saving 381 per month. So by means of integrating a two heat exchanger in between a condenser and compressor, and in between a evaporator and compressor, we are saving 381 rupees per month of your running cost. So that is the outcome of the this proposed pilot plant. Now, next, instead of running this entire thing by means of electrical, we are trying to run the entire thing by means of a PV operator models. So we have installed a PV models which have power consumption, power production of equivalent to running cost of the cold storage, as well as we have various components, blower and pump, and various measuring devices also running. So all the capacity we have calculated, and we installed 6 500 watt PV panel at the top floor. And initially we think of to have directly connected with the battery connector and directly connected with the cold storage. But thinking about the condition of the battery and power fluctuation of the battery, we laterally connected directly, grid connected with the electricity bill. So we have calculated the total electricity consumed by the cold storage along with the blower and pump, and that will be connected with grid operated solar PV panel. There also PV panel also, the main drawback in the PV panel is apart from efficiency, due to high heat absorption of the PV panel, especially in hot climatic like India, as well as hot climate in Madurai, the efficiency will be very little bit. So normally the efficiency of the PV panel is between 10 to 15% because of the high heat absorbed. Particularly after 2 o'clock, the radiation heat effect is also more. Therefore, we have to essentially going for a cooling arrangement to increase the electrical efficiency of the PV panel. For that, we have tried some 3 methods. That is, first we tried for a heat pipe. Yeah, heat pipe is nothing but a coil like this. This is called as evaporator side, and this evaporator side is connected with the condenser side. Another heat pipe is there, a long pipe, which will be filled with R134 as a refrigerant. The working principle is very simple. Actually, this evaporator side, this is the evaporator side, which is placed behind the solar PV panel, which absorb heat. Therefore, the refrigerant liquid will be evaporated because of absorbing heat. So that's why we call as this is evaporator section. This evaporated refrigerant vapor by gravity, it goes upward and it goes to this condenser. This is a condenser heat exchanger where we are using for heating the water. Yeah, just like a solar water heater. So we have a water heater tank where we place a condenser coil. That hot refrigerant vapor liberates its heat to the water where the water gets heated. Therefore, there are 2 advantages we are getting. We are reducing the temperature by 1 to 5 degree. Thereby, we are increasing the electrical efficiency of the PV panel. At the same time, we are getting a hot water production. So that is the outcome. For that, we are using a small test PV panel of capacity 165 watt capacity, and R134A as working fluid we are using. And the outcome of the results are, number 1, we are having an increase in panel heat efficiency, water power consumption, power production by 113.6 watt, whereas conventional is producing only 113.6, whereas our alternate arrangement will give a power consumption of 120.9 for this small solar panel, for this small panel. And also we have a continuous hot water from 31 to 47 degree temperature rise. So nearly initially the electrical efficiency is 9.3. Now it was increased to 9.9%. So that is the first advantages. Second, I have a hot water of 47 degree of capacity of 36 liter per hour. So yeah, 36 liter per hour of water I am continuously getting by connecting with a heat pipe with a temperature of 47. So that is another advantages. And compared to the electrical consumption, power production, the conventional will give a amount of 1561 as a net outcome of electrical power, whereas 1673 we are increased the power amount by connecting with the heat pipe technology. Nearly 112 for increase in amount by placing this. So that is the first outcome we are getting. But the main drawback of connecting the heat pipe is the connection of heat pipe, that is pasting the heat pipe at the bottom is very difficult. We found very difficult because we have to go for thermal grease or some other paste. But the backside of the PV panel is made up of glass, and it is very difficult to fix the glass panel with this heat pipe. And due to the load, automatically the heat pipe will be somewhat the paste will be break down, and therefore there is no perfect contact between the heat pipe as well as PV panel. So almost what result we are getting is only the 60% is nearly over 40% of the heat will be lost because of not perfect contact between the heat pipe as well as PV panel backside. That is the main drawback. Even though we have mounted like this by means of a strip like this, and we have screwed this, and we have making a tight arrangement to have a perfect contact between the PV panel bottom as well as heat pipe, we failed to get the good results. So that is the first outcome we are getting. Then we have tried for a water cooling effect. Before that, we tried another method. Instead of having this, we are trying the evaporator cooler. That is the principle of evaporator cooler in the PV panel. For that, we are just placing a small water tray at the bottom of the PV panel. So this is a small water tray. This is a small water tray which is placed at the bottom. The water will be absorbed by means of sack material, gunny bag sack. By capillarity, it will rise, and that will be fixed at the bottom side of the PV panel. During daytime, the solar radiation falls here. The water will get heated, and heated water vapor, pure water vapor, will goes to the bottom side of the PV panel, where it condensed. And by means of this incline, the condensed water will get dripped like this, and that will be collected with this collection trap. And what we are getting is 100% distilled water. At the same time, I am getting a 100% distilled water. At the same time, I am having a cooling effect of PV panel. So that is the main advantages. We are having a PV panel integrated, what we call the solar still. So a very simple principle. Even we can treat this any type of solid saline water or any waste effluent we can treat, and we can purify it as a drinking water. At the same time, the PV panel gets cooled down. For better exposure of the PV water, we have an extended surface where we place a glass surface here. Because only radiation effect, when heat absorbed by the PV panel, the water will be heated only by means of radiation heat. Direct heat will be penetrated by means of the glass surface, which will be extended along the PV panel. So that is an additional idea we have included here, and we have a good results. The better result is the temperature of the fluid bath is increased from 31 to 47. That is the water thing. Sorry, this is a results of heat pipe. Sorry, yeah. We have a maximum power increment of 9.8 watt by using the same type of the 165 watt of electricity power consumption. The maximum increment we are getting as a 9.8, and averagely the power is increased to 5.62. That is a notable outcome. In addition to this, we have a water collector of 120 ml for a particular hour. That is a maximum fillers between 1 to 2 alone. We have a 120 ml of water collection, and for the entire operation from 9 to 5, we have a nearly half liters of water we have collected. So additionally, we have water collection, and we have increased the electrical efficiency by using the PV panel integrated solar still. This is another type we have tried. Then we go for using a water cooled top surface. So why can't, instead of using this, why can't directly we are making a flowing water along the top surface of the PV panel? So that also we have tried for a very little laboratory model of 25 watt. And for that, we are using a small submersible pump of 18 watt submersible pump. This is a setup arrangement. So there is a small PV panel here. The water will be collected in a collection channel like this, and that will be overflowed, and it is made up of flowing uniformly along the top surface, and that will be collected by another tray, and by using the submersible pump, again it is collected. So this is a simple experiment, but compared to heat pipe, we are getting the better result, but there is a disadvantage. I will tell you later. The results what we are getting is nearly having a water flow rate of 2.3 kg per minute. We are having a maximum power production of 21 watt, and 5.3 kg minute of water flow rate. We are having a maximum power consumption of 22, power production of 22 watt, whereas conventional will give only 19 watt. So we are having a rise in 19 to 22 at the maximum. Compared to the power consumption of the submersible pump and all the things, we are having a saving of 10 watt 30. So that is a outcome what we are getting by using a small this PV panel of a simple capacity of 25 watt. But again, we experienced a problem of having corrosions because corrosion will be more for water because due to thermal stresses, the corrosion and causes the damages of PV panel surface as well as the pipeline and everything will be corroded. So that is the main drawback we have got. Then finally, we think of switch over the pilot plant to have a cooling with the air. So finally, we decided to have a bottom cooling by using a airflow rate. For that, we fixed a small fan, which is fixed and that air will be blown at the bottom surface of the PV panel. This is the top surface of the PV, and this is the bottom surface. The PV air will be circulated like this. To have better turbulence, we have tried some 2 baffles are placed inside the duct flow. The buffers is also designed by means of having various literature survey with choosing a better baffles having high heat transfer rate with low pressure drop. So that is the advantages. That is the things we are going to do. Periodically, we measure the temperature by using thermistor. We measure the velocity drop and we have compared the results. So here we have a pilot plant of 535 watt of photovoltaic panel we are using. Actually, we fixed 6 535 watt PV panel in series connection. And for testing, we have air cooling for 1 PV panel. And we are comparing the study with the conventional PV panel, which is running parallelly. A small fan, 140 watt rating DC fan, we are using to circulate the airflow rate. So this is a setup diagram. That is a small changes we have made. So in this duct we fix the fan. The fan will the air will be flow like this. This is the bottom of the PV panel. At the top you have a PV panel is there. And the electrical efficiency we are measuring by means of a PV analyzer, and that the various temperature and voltmeter variation we are measuring, and we are varying the flow rate by means of varying the variant by using a transformer. So this is a fan we fixed at the front side. This is the top view. So these are the various reference plan, and this is the panel which having a air cooling with the bottom. The air velocity also be calculated by fixing an anemometer at the airflow at the duct, and we found 2 suitable insert which will be placed inside the along the direction of flow. There are 3 positions we fixed, the 2 type of panel insert. The one insert is a simple design like this with a hole. This is the arrangement for that. The second is we call as a WV winglet. We call as a V winglet, which is connected with a small rod, and that will be connected like this. In 3 positions along the flow direction, it will be fixed. This causes the turbulence, most turbulence effect, and better contact between the PV panel as well as the airflow causes increase in efficiency of the PV panel. So this is a 2 panel, 2 insert we have decided to connect with the PV panel at the bottom cooling. And the results are very interesting. Actually, our outcome, we have to find out better outcome with electrical consumption, considering the electrical consumption of the fan also. For that, first study, we have vary the mass flow rate. By varying the mass flow rate, we found that the system is working with the very best with higher solar radiation. Of course, that is natural. So more radiation, more power. So net power output is better when we have higher solar irradiation. At the same time, we have a better results for a mass flow rate of lower mass flow rate, especially 0.38 and 0.28. The first 2 lower mass flow rate will have a better power increase. So you have to send the flow rate with the 0.28 or 0.38. We will have a better power consumption. That is the outcome we are getting. That will be proved for all the solar irradiation. all the solar irradiation starting from 700 to 1100, it is best. That is the first outcome we are getting. The second outcome is the temperature is dropped to a maximum of 11 degree. The temperature at the bottom of the PV panel is dropped to maximum of 11 degree for the flow rate, that is middle flow rate 0.38. For a particular highest solar irradiation at the Madurai 1100. This experiment was carried out during the last April to May 2024. We have increase in power output. 303 is the result what we are getting, whereas the conventional only gives 157. That is another thing. Third thing is considering the power consumption of the fan. Only the lower mass flow rate will compensate the power consumption of the fan also. If I am using such a setup, and if you are running with a lower mass flow rate of 0.28 or 0.38, I can save energy even though your fan is running continuously. That is the outcome we are getting. So, overall, we have increased the COP of the existing cold storage of 0.5 ton of refrigeration. At the same time, a raw effluent will be treated and it is converted into desalinated water. That is the second thing. Running the PV panel, running the cold storage by using a PV panel and thereby enhance the efficiency of the PV panel. That is the third results. And finally, our outcome is to disseminate the concept to through webinar like this. And we have multiple contact with our ISHRAE peoples because some 2 or 3% helped us to design and discuss. For each discussion, some 3 to 4 experts from Madurai ISHRAE is involved. One, Mr. Kishore, he is attending the webinar. He is a HVAC consultant, and another Mr. N. Balachandran is a cold room consultant. And one of my students, thank you, Mr. Rishi, he is also involving more in this experimental work. By using this, the final outcome is I am disseminating the concept through webinar, publishing paper in both ISHRAE as well as international journal also. And all the international journal we published, we have acknowledged the ISHRAE for funding. So these are the 4 journals we have published for ISHRAE. 3 published, and we are waiting the result for the 4th one. These are the Q1 rated journals we have published. About 4 journals we have published, and we are waiting for remaining 4 results. Thank you. And also we have given some international conference also based on the results. And all the results we have acknowledged the ISHRAE. Thank you. Thank you, Mr. Any queries? Some of them raise hand. They can ask. Madam, is it clear? Hello. Ritu, madam. Hello.
Yes, sir, you are audible.
Yeah.
You can see the questions on a Q&A section.
I think just a minute. Yeah. Thank you, Mr. Manogaran. They have asked the saving per ton of refrigerator. Of course, we have run the cold storage for 0.5 ton of refrigeration. For the 0.5 ton of refrigeration, about 300 rupees we are saving per year. That is a saving for running a 0.5 ton of refrigerator. Then Mr. Nilesh asked about the size of the humidifier. Normally, we fix the size of the humidifier based on the literature, but positioning of the packing material inside is not at all given in any of the literature. That is the only thing research gap we have tried. So normal size is 1 meter cube. 1 meter cube of the humidifier we have designed based on the literature available on the things. And positioning of the packing material only we decided. Positioning is far beyond the air or nearest to water flow rate. Positioning, we can fix the packing material, we will get the better result. Is it possible to have a commercialization? Thanks for Deswar Singh. Actually, we are trying for commercializing with our one of the cold storage consultant, Mr. Balachandran. Actually, we have still running the setup with some other modifications also. Probably, even though we have submitted the results and all the things, based on the, we have the entire setup is we are available. So we have further some modifications we made. Within another 6 to 7 months, we are going to implement with some available cold storage. That is definitely we are thinking of commercialized thing. And maximum temperature drop, Mr. Sukumaran Balaraman is asked, is maximum of 11 degrees. And unfortunately, when we found the results, after 1 to 4 o'clock, there is no much drop in temperature because of more radiation effect. The heat will be stored more. Therefore, the radiation will be affect more. Therefore, cooling is very difficult after 1 to 4. That is the outcome. But maximum we are reducing to 11 degree. And TDS is also reduces to about, we checked about 350 ppm. We have checked, and the pH value is also come into the normal range. Of course, so far I didn't tested with effluent, waste effluent. Actually, we have did a lot of experiment using waste effluent. For here, I didn't tested with the waste effluent because food material is involved inside the humidifier. I mean, cold storage. I didn't use with the waste effluent, but even we can use the waste effluent. And the ppm is reduced with this, but some odor is there. Some odor is there. Thanks to Mr. Nilesh. And can you suggest the use of heat pump for HDH deceleration? That also I am trying, sir. Actually, still it is a conceptual level I am having that, but definitely there is a chances of using heat pump. Actually, this idea is itself just like a heat pump. Actually, the condenser heat. In heat pump, we are using the condenser heat. I am retrieving the condenser heat by cooling by water, and that will be used for HDS. So, of course, this is a idea of a heat pump. In heat pump, we are using only the condenser heat, and we are not at all bothered about evaporator. But here we are using the evaporator heat also, as well as condenser heat also. Even we can go for air conditioning also. Then same question. What is the temperature of water before spraying in any other of maximum case? It's an ambient temperature, sir. It is ambient temperature, and by absorbing heat, it rises up to 35 degree. 5 degree rises there in heat exchanger. Thank you, sir. And that is 5 degree rise, sir. Satish Kumar, sir. Maximum 5 degree rise we are getting from the condenser. Thank you, sir.
So thank you, Dr. Srithar. You have done really so many combinations to come to a find a solution, truly research oriented. So I think we are done with the questions.
Yes, yes, madam.
Yes. So thank you very much.
Thank you, madam.
Yeah. So this is our third of the series, so that everyone listens and knows what is really happening, because many people ask, okay, you come ask us for money for research, so we want to know what is happening. So this is a good way, and possibly this recording we will keep and maybe put it up on some research website which is getting developed. Okay.
Thank you, madam.
So thank you everyone who has attended. I hope you have some takeaways from this. Thank you very much, Neetu, for coordinating it.
Thank you, madam. Thank you, Nitu. Thank you, Nitu. Thank you.